All right, everyone, this is 327 from R.C. Hibbler's Mechanics and Materials. This problem, we're trying to figure out the Poisson's ratio. Let's go ahead and write this out. That's negative the lateral strain over the longitudinal. Negative because these are inverse of each other. Imagine some material being stretched out. As it's stretched out and increases in length, you can imagine the diameter of that material shrinking and become more compact. Likewise, if you imagine some wire and you give it some compressive force, you can imagine that the diameter would increase. Okay, so from this problem, we can go ahead and find our modulus of elasticity. Remember, rise over run. We have 400 over 0.002. So that turns out to be 200 gigapascals. Of course, I've skipped some simplification steps. I'm sure you can figure out. We have this load of 50 kilonewtons. That's where we're going to figure out what stress the material is actually subject to, right? So we have this 50 kilonewton force over some area. From the problem, we can see that the original diameter is 13 millimeters, right? So the area of this circle, pi over 4 times 0.013. Let's put this in meters so we can work with pascals, right? Okay. So that's going to simplify to 50 times 10 to the 3, 50 times 10 to the 3 over pi over 4 times 0.013 squared, or 376.698 megapascals. So we can see this below the yield strength, but anyways, in this problem, we're not even asked to deal with anything like the permanent set or anything along that line, so we don't really need to worry about that. But what we do need to know is the Poisson's ratio. This change in diameter is going to help us figure out the E lateral. If you remember my talk a little bit ago about the wire, and you compress it and the diameter expands, or you elongate the material and the diameter might shrink, right? But we can go ahead and find the longitudinal first, and then we're going to use the change in diameter to figure out the lateral. So let's find this longitudinal. Now we divide that by E, the modulus of elasticity, which we found to be 200 gigapascals. That's times 10 to the 6th, and that's times 10 to the 9th, right? So let's throw this in our calculator real quick. 376.698 times 10 to the 6th over 200 times 10 to the 9th. And that gets us the longitudinal to be 0.0018839. We're writing out all the digits in this intermediate calculation so that we know our final answer is going to be all right. Now we can move on to the lateral strain, right? So for this E lateral, you want to consider the change in diameter over the original diameter. So let's do 12.99265 minus 13 over 13. Now we plug this in our calculator and we get this lateral to be negative 0.000565385. And of course we could skip this part. Now this Poisson's ratio is negative of this value over this value, right? So we have this negative 0.000565, and you may save some time here by just simply knowing that both of these you could write as times 10 to the 3, but I will write it all out for simplicity. And you'll equate that, and you'll get that you have a Poisson's ratio of 0.3.